Class, today we are going to look at root locus. Okay, now root locus, when we talk about root locus, this is a graphical representation of the poles of a closed loop system as a parameter of the system changes. So if we have a closed loop system, for example, if we have K, G of S, H of S, this is minus plus, of course, E of S, R of S, and our C of S. Okay, then we know that T of S equals K G of S divided by 1 plus K G of S H of S. Okay, so the poles of T of S can be found by solving the equation one plus K G of S H of S equals 0. That's the characteristic equation. Okay, so obviously what can be seen from this is as the K changes, and K is a system parameter that way, as K changes, then what will happen? The poles will also change. Okay, so the changing, so let's say if I select values of K, let's say K equals 0, 5, 10, 15, 20, 25, 30, 35, and so on and so forth. And then when I plug in any value of K, I'm going to find the corresponding poles for the system. Okay, so when I do that, then that is going to give me the roots for that particular value of K. So for 0, I'll get some roots for 5, 10, 15, 20, 25, 30, and 35. And when you plot them, you will see that they follow a particular path. And this is what we call the root locus. Okay, so we'll deal with more about that later. You get to understand it. Okay. Now, this is a very powerful tool that we can use for the analysis of transient response and also for stability design. And usually when we are dealing with feedback control systems, it's very difficult to comprehend from the qualitative point of view, and therefore you have to rely heavily on mathematics, like we have seen in the previous chapters. Now, instead of relying heavily on these mathematics, with the tool called root locus, we are able to both visualize both quantitatively and qualitatively the roots behavior, and that helps us to be able to appreciate the behavior of the system without having to rely heavily on mathematics. Okay, so this root locus, okay, in the previous chapters, like the units that we have dealt with earlier, you will see that we were looking more at first and second order systems, and all the equations and expressions we derived for the transient behavior of a system relied heavily on first and second order systems. And then also even some of the other stability things we talked about were second and lower order systems, because if you have higher order systems, then factorizing of the characteristic equation becomes something that is a little tedious. Okay, but then the good thing about root locus is that it's going to help us to be able to analyze and design the transient response and even the stability of systems or higher order systems like third order, fourth order, fifth order, and so on and so forth, without having to go through all the tedious mathematics. And we can even, under some desirable conditions, we'll be able to use it to design the settling time, the overshoot, and the like. Okay. Another thing that the root locus can help us to do is to know the performance of the system in terms of stability. Okay, so with the root locus, we'll be able to determine the range of values of k for which the system is stable, the range of values of k for which the system is unstable, and be also able to know when it breaks into oscillation, and that is when it crosses the imaginary axis. Now, before we discuss root locus, there are some key concepts that we should understand. And this, I'm going to talk about two concepts, so two main concepts. Okay, and these two main concepts, the first one will be to discuss the control systems problem. So I've already touched on this, okay, and that is when I drew the system above, okay. So let's say you have this system and you are supposed to find, okay, so looking at this system, we see that the open loop poles, so when we talk about the open loop transfer function, it is given by G, K, G, H. So K, G of S, H of S. Okay, this is what we call the open loop transfer function. Okay, and it is okay. It is very easy to see that the poles of the open loop transfer function can easily be known. Okay, and the reason is because most often these are physical systems. These components are physical systems, and being physical systems, they are usually first order or second order systems, and so this is going to form a concatenation of the transfer functions whose poles are already known. Okay, and therefore, because we know the poles of the system, and the systems are first and second order systems which can easily be factorized, when you concatenate them, the overall poles can also be known easily. However, once we put it into a closed loop and we get over 1 plus K, G of S, H of S, then there is a problem because the roots of the denominator cannot easily be known. Okay, so the roots, so the poles cannot be known easily for higher order systems okay, so the poles cannot be known easily for higher order systems, okay, because for higher order systems we will have to factorize the polynomial, and if we have computers we can use that, but let's assume you don't have a computer, and then you find a way to factorize that, and after factorizing that, for a value of k you have to plug in another value of k to factorize, and so on and so forth, and this is not very simple. To even throw more light onto that, let's assume that our g of s can be represented as the numerator of g of s divided by the denominator of g of s, and our h of s can be represented by the numerator of h of s over the denominator of h of s. Okay, if that is the case, then our t of f will be given by k and g of s and h of s, all divided by dg of s dh of s plus k and g of s and h of s. Okay, where this our d is the factored polynomial, signifying the denominator, and n is the factored polynomial, signifying the numerator. So in other words, g of s is made up of a polynomial divided by a polynomial. So the ratio of the numerator polynomial and the denominator polynomial, and the numerator polynomial is the ng, denominator is the dg. So we see from this that the zeros of t of s is known easily because they are, okay, so that is going to be the same as the zeros of the open loop transfer function. Okay, okay. However, the poles of t of s are not readily known. Okay, so poles of t of s not readily known, and also poles of t of s, as it can be seen from there, changes or change with change in k. So when I change k, the poles are also going to change. Okay, and so this is what makes the control system problem a little difficult. Okay, so if we actually desire to know the behavior of the system, then we can only know the system performance okay, by factorizing the denominator for the given value of k. So for every given value of k, if we want to know how the system will behave at that gain, we need to first factorize the denominator, which is the characteristic equation, that is k. So actually in the broken down form is going to be this dg of h of s dh of s plus k ng of s nh of s must be factorized. Okay, it must be factorized. So you must factorize that for a given k. So this is the problem we are faced with, and so we look for a simpler system of handling this without having to be factorizing. So if I have, for example, 100 values of k, and I want to know how the system will behave at any of the 100 values, then I need to be plugging in each of the k values, factorizing the system before I will know. Now this is not, or this is very tedious for higher order systems. The second concept that we want to understand, and this is very important because this concept actually is going to help us with everything else that we are going to deal with when it comes to root locus plotting and refining and even calibration. Okay, so, and that concept is complex. So vector representation of complex numbers. Okay, so vector representation of complex numbers is very important. Let's take a complex number okay, sigma plus j omega. Okay, and this complex number can be represented as a vector. So I'm sure you have studied this earlier in your algebra class. Okay, and this vector will have a magnitude and angle. Okay, so let's call the magnitude m, and then let's call the angle theta. So the vector can be represented by this complex number, and of course if we plot it, then it's going to be of this form. Okay, where we have this as omega, j omega, and this is our sigma. J omega as this, sigma as this. This is our sigma, this is j omega, and this is going to be that vector. Okay, so the vector will be from here to that point. Okay, we put a dot here. Okay, and the magnitude is going to be the m, and the angle it makes with a positive axis, real axis, is going to be theta. Okay, now let's take a function, given a function f of s, where s is a complex number. Okay, given a function f of s where s is a complex number, then it can be shown that f of s is also a complex number. Okay, if s is a complex number, then f of s is also a complex number. For example, if I have f of s equals s plus a, okay, then it means the zeros of f of s equals minus a. Now if I substitute my, substituting my s equals sigma plus j omega into f of s, then I'll have f of sigma plus j omega equals sigma plus j omega plus a, which is sigma plus a or plus j omega. Now I can plot this as a vector, in which case the real axis is going to be, if this is sigma, is going to be here. Okay, so let me put this as a and this as a plus sigma, then it's going to be something like this. Okay, so this j omega, I have my vector here. Okay, so that's how the whole system will look. Okay, so I can, this is actually also equivalent to plotting a system like this, where my pole is here, minus a, okay, and my sigma is here, sigma, and this is going to be my j omega. Okay, and then I'll plot it from here. Okay, so the only thing I've done is to translate the j omega axis, okay, from 0 to a. Okay, so a is now at where a was is where the 0 is, therefore the left hand is going to be minus a and the right hand is going to be sigma. So this is another representation of the system, and this tells us that if you evaluate f of s at f of s equals s plus a at s, a point s, which is a complex number, then it is the same as drawing a vector that originates from the 0 of f of s and ends at the point s. Okay, so for example, if I have my f of s equals s plus 10, okay, if I evaluate this, so find f of 2 plus j omega, and omega is, let's say, 2, then this is going to give me 2 plus j 2 plus 10, which is 12 plus j 2. Okay, but I can plot this one as the magnitude, so this will be 2, okay, and then this is going to be my 12, so this is the vector. Okay, but another way of plotting this is first to locate the 0, which is, so if this is 2, 4, 6, 8, 10, then I'll locate the 0, so this is the 0, then I'll locate the point, so this is 2, and this is 1, 2. Okay, so let me locate the point s, 2 plus j 2, and I'm going to draw a vector from here, to that point. Okay, then I can easily find the magnitude, okay, which is going to be equal to square root of the distance from here to here, which is going to be 2 minus minus 2, that is 2 minus minus 10, okay, and then the distance from here to here, from this side to this side, that is going to give us 2 minus 0. So that will be square root of 12 plus 2 squared each, that is square root of 144 plus 4, that's 148. Okay. The same wise, the angle will be tan, so the angle will be here, theta. So theta will be equal to tan inverse of the distance up here, which is 2, divided by the distance down, which is 12, or 2 minus minus 10, and that gives you tan inverse of 1 over 6. Okay, so that you can easily compute. Okay, so then with this idea, we can now write as our f of 2 plus j2 equals the magnitude square root of 148 angle minus tan inverse of 2 over angle tan inverse of 2 over 12, or 1 over 6. Okay, so this is the vector that represents the function f of x equals s plus 10 evaluated at 2 plus j2. Of course, you can do this by just substituting direct and finding the magnitude and angle of this, and you will see that it's not different from what we have here, except that this helps us to find it with vector, the application of vectors. So what is the usefulness of this application? So we are going to apply the concept to complicated function. Let's take a function f of s equals delta as I move from 1 to m of s plus zi, where z are the zeros for the system, over product of as j move from 1 to n, s plus po j, okay, and this then is the product of the numerator, is complex factors, all divided by the product of the denominator. The denominator is complex factors. So if you have the factors of the numerator and the factors of the denominator for the system, then you can easily write the function in this form. Okay, now you can see from here that note that each factor in the numerator and each factor in the denominator, okay, is a complex number. Okay, so each factor is a complex number, and the complex number that can be represented as a vector. Okay, so each factor is a complex number, and that complex number can be represented as a vector, and each vector has a magnitude and an angle. Okay, and so it means that if we want to evaluate that function, then we can represent it as the magnitude of f of x at any point s can be given by, so the magnitude of f of s at any point s can be given by m equals the product of the zero's length, because the zero length for each one is the magnitude of that particular factor, divided by the product of the pole length, because the pole length for each one is the magnitude of that. So for example, as we saw from the top here, you see that the zero length will be from this -10 all the way to this point, and that is going to be the magnitude. So, and if it's a pole too, is going to be the same concept. So you get this, and that is going to be equal to a summation from I equals 1 to m into s plus zi magnitude over the product of j equals 1 to n s plus pi, again the magnitude. So we plug in all the pi's and then we evaluate. So it pretty much is the product of all the zero lengths divided by the product of all the pole lengths, and that is going to give you the overall magnitude for the system. Also, if you evaluate f of s at any point s, so at any point s, the angle theta of f of s is given by theta equals summation of the zero angles, the zeros angles, minus the summation of the pole angles. So you sum all the zero angles, and then you subtract the summation of all the pole angles, and that is coming directly from the complex number concept that we have up here, and then that is going to give you the overall angle for the complex number. And then you can express your f of s as your magnitude theta or angle theta. It means that your theta is equal to a summation from I equals 1 to m, the angles of s plus zi minus summation from j equals 1 to n, angles of s plus pi's. So that is going to give you the overall angle for the system. Note that when we talk about a zero's angle, then that is the angle measured from a positive extension okay, of the real axis. Okay, it simply means if I have, for example, 1 0 here, another 0 here, okay, and then the point S is, let me draw another 0 maybe, let me draw it here, okay, let me use the one on the real axis for now. So this point S, if I draw my 0 like this, then the magnitude is here, the angle is the angle here, okay. This is the positive extension of the real axis, okay. So that's the positive extension of the real axis, so the angle becomes theta here. So that is what we mean by zero angle. The same thing applies to pole angles. So if it's a pole and the point is S is here, I'm just going to join like this, okay, and then the angle here becomes the pole angle. So zero angles and pole angles, we can easily find them. Let's use an example to illustrate that. Okay, so let's evaluate the complex number or complex function f of s at s, okay, where f of s is given by s plus 1 over s into s plus 2, okay, and s equals minus 3 plus j4. So this can also be stated as f of x equals this, find f of minus 3 plus j4, okay. Now this, we can solve it as first plotting. So we can do a plot, okay, and then let me go. One, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, okay, and let me go 1, 2, 3, okay. So this is j1, j2, j3, okay. So this is 0. So what can I do? Well, I'm going to find a point S, okay. So let me add 4 to it, j4. The point S, okay, so unfortunately, okay, let me, okay, and then let me move this down a little bit, okay. So the point S is actually going to be somewhere here. S is minus 3 and j positive 4, so this will be S. And so the poles are going to start from 2, move to S, okay, because we have one pole here, then we have one pole at the origin that will also move to S, then we have 1 0 at the negative 1 that will also move, okay. So then what will be the angles? The angles will be this angle, that angle, that angle, okay. So that will be the angles. So this will be theta 1, theta 2, theta 3, and the magnitudes, let me call this A, B, and C, okay. And that is going to be equal to the magnitude of S, the magnitude of S plus 1, and the magnitude of S plus 2, Okay, so that's basically what it will be. So how do we solve for f of minus 3 plus j4 is going to be equal to the magnitudes b over a times c. Okay, so a and c are the poles you divide, and then b is 0, and then the angle will be theta 1 minus theta minus theta 1 plus theta 2 minus theta 3. Okay, so that basically will be the angle. Okay, so if I want to solve this, it's going to be simple. From the top, the magnitude for the a will be equal to, the real axis is going to be, so square root of, the real axis is going to be 3 minus 0, or squared. We are just finding the angle, okay, but you can say minus 3 minus 0, it doesn't spell anything. Okay, so if you want to do it that way, minus 3 minus 0, and then you find square, plus the imaginary axis. Okay, and the imaginary axis is going to also be what? 4 minus 0, all squared. Okay, and then the angle will be 180 minus tan inverse of, okay, 4 minus 0 over 1 minus 0. Okay, so that will also give you your angle. Okay, so now we are using 180 minus because we are actually finding this small angle here, and then we'll subtract that one from 180 to get us our angle theta 3. Okay, so b will be equal to, again, b is going to be, and so this is going to give us about square root of 17, 3 minus 0, and then 4 minus 0, sorry, that will give us 5 angle 126.9. okay, and then the second one will be when we find b. Okay, b is at zeros, so b is the zeros, then you get square root of 3 minus 1 squared plus 4 minus 0 squared, and then the angle 180 minus tan inverse of, again, 4 over 3 minus 1, and that is going to give us square root of 20 angle 116.6 degrees. And then our c we can evaluate to be square root of 3 minus 1. Okay, so we get 3 at this point, minus c is minus 2. Okay, so 3 minus 2 squared plus 4 minus 0 squared, angle 180 minus tan inverse of the adjacent angle. So this the magnitude of the adjacent, which is going to give us 4 minus 0 over 3 minus 2, and that will give us square root of 17, square root of 17 angle 104.0 degrees. Okay, and therefore if we find our m to be given by square root of 20, okay, divide by 5, square root of going to be square root of 20 times square root of 17 over 5 square root of, oh no, just over 5. Yes, so it's going to be the pole. So the pole is going to be given by square root of 20 divided by 5 square root of 17, and the angle will be into 116.6 minus the angle of the 0 minus 126.9 minus 104.0, and that will give us the value to be 0.217 angle minus 114.3 degrees. So that would be how to evaluate the system, and you can go and check this by just substituting and solving for the value and finding the angle and the magnitude using complex number approach. Okay, so for assignment, I want you to find, given f of s equals s plus 2, s plus 4, all over s into s plus 3, s plus 6. Okay, I want you to find f into minus 7 plus j9 by using A, the direct substitution, and then B, using calculating the results using vectors. Okay, and your answers, or your answer should be 0.096 angle minus 110.7 degrees. Thank you very much. We'll move from here to root locus and apply the concept.